One of the frequent goals that we have when doing statistical inference is to try to understand or get at or guess the value of a parameter from some population using data to inform that guess. Right? So very often we're going to want to say, what is the value of that parameter in the population? We can't know exactly, so we take a sample, we collect some data, and then we want to use those data in order to make a guess, make an educated, informed guess about what the value of that parameter is likely to be. This is a process that is known as estimation, and estimation is going to give rise to estimators and estimates. And so there's sort of a lot of terms that are bouncing around here around this process of estimation, and we want to try to pull apart and understand how does this process of estimation work, and what do we need to know about it. So within statistical inference, estimation refers to the process of making an informed guess about the value of a parameter. And when we're talking about it being informed, we're talking about using information that we've been able to collect from a sample or from an experiment or so forth. And so if we take in those data and then use those to make a guess about the parameter value, then that is the process of estimation. So the three sort of main concepts we have going on here is estimation, which is the process, and then we have estimators and estimates. And so we want to try to tease apart what we're actually discussing with each of these concepts. So with estimation, again, it's the overarching process. We're attempting to use observed data to make predictions about unknown parameters, right? We want to be able to say, we think that the value of the parameter in the population is this, and it's based on data or information that we've been able to gather. In general, estimation can be sort of referring to a whole class of different problems, but when we're thinking about it, in this context at least, we're normally thinking about a specific type of estimation referred to more broadly as, or more specifically as, point estimation. So by point estimation, we mean we're trying to guess the value of a single point, right? One parameter's value, or a couple of parameters' single value. We're not trying to guess a range of values, we're not trying to output some type of interval, but we are just trying to guess the single value that a parameter takes on. And so because of that, it's a point estimate. Okay. If you hear the term estimation by itself, it's almost certainly referring to point estimation, right? And so the most common way that we'll use estimation is for point estimation, but if you want to be more specific, we are technically doing point estimation here. Any process or mathematical function that takes in data and then approximates a parameter value is, in theory, useful for estimation, right? So there's not going to be one way of estimating a particular value, right? Estimation can proceed with any process, algorithm, mathematical function, as long as it's taking in data, and then whatever it outputs is a guess at a parameter value. The functions that we're actually using here are referred to as estimators. So whenever we hear estimator, we're thinking that's a mathematical function, that is a mathematical procedure, that's a process that we can actually follow. It's going to take in the data and output a guess at the parameter value. Okay? And so when we're talking about estimation, estimation is the overarching subject. It's the process of trying to guess the values. Estimators are the mathematical functions that are actually going to provide guesses for these values. Estimators, importantly, are a type of statistic, right? Statistics are functions of data, and so estimators are going to be taking in data and using those as a function, so they are statistics. And specifically, they are statistics that approximate parameter values, right? And so a estimator is a statistic that's going to approximate a parameter value. Any statistic could possibly be an estimator, and we're only really differentiating between these two concepts because statistics themselves are just summarizing something in the data, whereas estimators are designed to specifically be tied towards some specific population parameter. Now, because statistics are random and estimators are just statistics, that also means that estimators must be random. And as a result, estimators have a distribution, and specifically it's going to be the sampling distribution, right? So the estimator's distribution is the sampling distribution of that estimator. Now, when we apply an estimator to actual data, so you've gone out, you've actually collected a sample of data, and then you apply the estimator to it in that case, it's going to produce some specific value, right? You're going to take in the actual observations, you're going to plug those into the function or the algorithm, it's going to output some number, right? And that number, that's the guess that you have towards the parameter value. When it produces that specific number, that is called an estimate. Okay? So the specific value that is produced by an estimator is referred to as an estimate. So to differentiate these three concepts, just summarize what's going on here. Estimation is the process through which we're going to try to guess at the values of parameters. Estimators are mathematical functions that take in data and output values. Because they're functions, they're random, they have their own distribution. Estimates are specific values that are produced by estimators. So when you actually take data, you plug it into your estimator, it gives you an estimate. Okay, so we'll focus on differentiating between these. It's a lot of jargon and it's a lot of statistical terminology to get used to, but they're important to be able to convey the subtleties between the different points. So estimators are the mathematical function or process used to perform point estimation, right? They are random, they're the actual function that is going on here. Okay, so they're statistics, they're random with sampling distributions. Estimates are the specific realizations of our estimators. They're specific numbers, right? An estimate is always going to be some number. Right? It's not a mathematical concept. It's 3 or 7 or negative 52, right? There's some number associated to an estimate. We can view estimates as draws from the sampling distribution. So whenever you observe an estimate, you can say that's a realization of my estimator. That is coming from the sampling distribution of my estimator. And remember that every time you take a sample, there's going to be differences within that sample, right? There's sampling variability. And so the estimator's distribution comes because of the sampling variability, right? That's where the sampling distribution emerges from. And because of that, the estimate is contingent on the specific sample that we happen to see. Right? If you get a different sample, you're going to get a different estimate. And so the estimator, it stays the same. It's just the process. It has some distribution, but your estimates, those change every single time that you take a different sample. So estimators are used to compute estimates in order to approximate the value of a parameter. Estimators are the function. Estimates are the specific values. Let's walk through some examples just to make sure that this is as clear as can be. So the first example we could think about is the sample mean, right? So if we consider taking a sample of size n from some population, then we can take the sample mean to be x bar here, right? X bar given by 1 over n times the sum between I equals 1 and n, right? So the sample mean, when expressed in this way, is a random quantity, right? It's a statistic. It's a mathematical function. If I give you a bunch of values for x, then this can give you a number, but by itself, it's not a number, right? It is just the function here. And so because of that, the sample mean is random. It is a function. It is an estimator, right? So this is an estimator. And in particular, we normally think about the sample mean as being an estimator for the population mean. So by calculating the sample mean, we hope that we're going to get a value that is close to the population mean. If we were to actually take a sample of size 10, we find the sample average to be 3.5, then this is an estimate. And when we have an estimate, we always write those using lowercase letters, right? And so if we think about what's going on here, right, when we have our estimator, x bar, we write that with a capital X. When we actually observe specific numbers, we're writing this with the lowercase x here, right? And so it's sort of an important distinguishing factor between those two. Lowercase letters are specific numbers. Uppercase are random variables. We can think about the sample minimum as a secondary quantity here, right? So if we consider taking a sample of size n from some population, then we can take the minimum, which we typically denote using this notation x with this 1 in brackets as a subscript, and that's going to just give us the minimum value between everything that we observe. Once again, when written in this way, this is going to be an estimator, right? It's a function. It takes in data, outputs a number, but it's not a number itself. And so this is an estimator. And we could think about this as being an estimator for the population minimum, right? If you want to know what is the smallest value in the population, then you could take this as an estimator for that. If we observe a sample of size 1037, find that the smallest observed value was 13.21, then this becomes an estimate. It is the estimate produced by our estimator. Notice that again, we're using lowercase letters here in place of the uppercase. So it's lowercase when we have an estimate, uppercase when we have an estimator. The sample standard deviation, right? So the sample standard deviation, if we consider taking a sample from some population, then the standard deviation is given by this expression here. There's a square root missing in this expression here, right? So this should actually be the square root of what we have there, right? But the point still remains that this expression down here is an estimator, right? It is a function that takes in data and could output some number. It's not a number itself. Because it's an estimator, it's random, it has sampling variability, right? We can talk about its sampling distribution, but it's an estimator, and probably an estimator for the population standard deviation. Now, of course, if we observe some specific sample, so a sample of size 314, we find a standard deviation of 1.59, then this is an estimate. Again, when it's an estimator, we write it with capital letters. When it's an estimate, we write it with lowercase letters. Right? Estimators are the functions. They are random. They get capital letters. Estimates are specific values. They're non-random. They get the lowercase values to go along with it. So we can think about the sample mean as being one specific estimator. We saw that in the examples listed there. Right? So the sample mean is going to serve as a point estimator for the population mean. If you wanted to guess what the population mean is, one of the ways you could take a guess at that is by computing a sample mean from some sample from the data. So the sampling distribution from the sample mean captures its uncertainty, right? And using the sample mean to compute an estimate allows for us to make informed guesses about the true population mean, right? And so not only are we sort of getting at what that value in the population might be, but we're informing it using data. Now, because of sampling variability, we don't expect that any estimate we produce is going to be exactly correct, right? We're always expecting that we're going to be a little ways off of the truth, right? And that's just the randomness of our samples. But the sampling distribution is going to allow us to quantify this level of uncertainty. So we're going to admit that, well, we're not going to get this exactly right. However, using this sampling distribution, we can say, well, how wrong did we actually get it? And so using the sample mean is going to be a method for performing point estimation, right? We can take the sample mean, we can treat that as a point estimator for the population mean. And it's going to be sort of a more rigorous way of doing this than to just sort of take a guess at what the population mean might be. And so the justification for using the sample mean in this way can be supported through the theory of estimation. And the real question that we want to answer in this way is, this process makes sense. It's sort of intuitive to take the sample mean and use that for the population mean. But is it going to be good? How do we know that we're actually going to get something that performs well? Right? And when we talk about it being good, what we're really thinking about is we want it to be close to the truth, but we don't observe the population mean ever. And so how can we know that what we're producing is actually going to be a good representation of the truth? How can we be sure that whatever we've collected from our data is going to somehow be representative of the real value out there in the real world? And so that's where this theory of estimation is going to come in. The theory of estimation is going to allow us to assess, is the estimator any good or not? Okay? And so the process of point estimation starts from estimators and estimates, and we're going to be able to build it up from there, right? Where you're going to actually be able to assess the quality of estimators. Estimators themselves are random variables. They are functions that take in data and produce estimates. Estimates are going to be the specific values. A really crucial part is going to be assessing how well these estimates actually perform, or how well these estimators actually perform, so that we can know when we get an estimate, is this going to be close to the truth or not?